Section 1.4 is all about friction. Any surface which exerts a tangential force, in other words a sideways force, is said to be rough. In other words, it has a frictional force acting along the surface. The force which acts at the point of contact with a rough surface has two components. There's the reaction perpendicular to the surface, known as the normal reaction force, normal meaning perpendicular, and there's this new component that we're going to study now, the frictional force, which we use capital F subscript R to represent. Now I know it can be confusing. We've got F for friction, we've got F for force, but if you get used to this notation, capital F subscript R represents the frictional force every time. Now also we have capital R, which we tend to use to represent the normal reaction force, and of course there's another word starting with R that we often see in these questions, and that is resultant. So please try and get used to the fact that R in this context represents the normal reaction force. So the friction and the normal reaction force are related in the following way, and this needs to be learned. The friction is always smaller than or equal to a quantity that we're going to study in a moment multiplied by the normal reaction force. So this symbol here is the Greek letter mu. It's a Greek letter mu. It's called the coefficient of friction, or more correctly the coefficient of static friction, because there are different types. And it's a property of the two surfaces that are in contact with each other. So depending on what the two surfaces are made out of, mu will be different values. Now mu is always more than or equal to 0. If mu was 0, then there's no friction and we have a completely smooth surface. In reality, there's almost always friction. So in reality, mu is hardly ever 0. The bigger mu is, then the more rough or the rougher the surfaces are. So if you've got two sheets of sandpaper and you're trying to rub them together, you're going to get quite a high value of mu because there's going to be plenty of friction there. But if you've got two blocks of ice and they're quite smooth and they've melted a bit and you're rubbing them over the top of each other, there's not going to be much friction there. Mu would be really small for those. So the value of mu depends on what the two surfaces that are in contact are made out of. The following summarize the properties of the friction force at a rough surface. First of all, the force of friction acts in the sense so as to prevent motion of a body. That is always true. If the body is moving to the left, friction will definitely act to the right. It always acts to try and prevent motion. B, until the magnitude of the force of friction reaches a limiting value, its magnitude is just sufficient or just enough to prevent slipping. I'm going to try and emphasize that through the following examples. So part C, at this limiting value, friction reaches its maximum possible value, and that will be equal to mu times R. Going back to the formula above, friction is always less than or equal to mu times R. So that means the biggest it can be is mu times R. D kind of links back to B. Until slipping occurs or until motion happens, then friction is either less than mu R or it could be equal to mu R. Again, I'm going to try and emphasize all these properties through the following examples. So a key point now, for friction equaling mu R, the friction is said to be limiting and the body is said to be in limiting equilibrium and is on the point of slipping. So friction is limiting, so friction has reached its maximum, and if the body or the object is in limiting equilibrium, that means it's delicately balanced and it is on the point of moving. We often use the word slipping when there's friction involved. Now let's look at the three diagrams we have here. I'm going to label them A, B and C. So diagram A, diagram B and diagram C. In diagram A, an object is sitting on a horizontal surface. There's the reaction force R and the weight of the object mg, and there's no other forces, so therefore there's no horizontal movement and there's no friction needed here. It might be a rough horizontal surface, so friction could act if it was needed to, but since there's no reason for this object to move horizontally, then friction doesn't need to act. So because there's no resultant horizontally, then there is no friction needed to keep this object where it is. In part B, same vertical forces, but now we have a T force pushing the object to the right, and F, that should have a subscript R, FR, so please add that onto your diagram. FR is the friction force trying to stop it moving. Now the purpose of this diagram in B is to say if there's no movement, then the frictional force will equal the pushing force, the 10, whatever T happens to be. So if there's no movement, then the friction can match the pushing force that's trying to make it move. Contrast that now with part C, where now we have motion. So this object now in part C is definitely moving to the right. So what must have happened is the T force must have increased to a point where friction could no longer match it. You can see we now have F max. So very importantly here, T is stronger than friction. Friction has a limit, has a maximum value. Once it reaches that value, it can't get any stronger. So if we have a pushing force like we have T in part C, and it is stronger than friction's maximum value, then the object will move. In fact, it won't only move, it will accelerate. There will be a resultant force, and as per Newton's second law, resultant force equals mass times acceleration. So that's an introduction to section 1.4. In the next video, we're going to move on to example 1.4.1.